In this section, we will conclude our discussion on glomerular filtration. Let us talk about the measurement of glomerular filtration rate. GFR is measured by the clearance of a glomerular marker. A glomerular marker has the following three characteristics. 1. It must be freely filtered across the glomerular capillaries with no size or charge restrictions. 2. It cannot be reabsorbed or secreted by the renal tubules. And 3. When infused, it cannot alter the GFR. Thus, the properties of the ideal glomerular marker differ from those of a marker substance used to measure renal plasma flow, such as PAH. The clearance of inulin serves as the ideal glomerular marker. Inulin is a fructose polymer with a molecular weight of approximately 5,000 daltons. Inulin is not bound to plasma proteins, nor is it charged, and its molecular size is such that it is freely filtered across the glomerular capillary wall. Once filtered, inulin is completely inert in the renal tubule, meaning it is neither reabsorbed nor secreted by the renal tubular cells. Thus, the amount of inulin filtered across the glomerular capillaries is exactly equal to the amount of inulin that is excreted in the urine. The clearance of inulin equals the GFR, as expressed in the following equation. Recall that the clearance of any substance is the urine concentration of that substance times the urine flow rate divided by the plasma concentration of that substance. Thus, the clearance of inulin in milliliters per minute is the urine concentration of inulin in milligrams per milliliter times the urine flow rate in milliliters per minute divided by the plasma concentration of inulin in milligrams per milliliter. Because of this handling of inulin in the renal tubules, the clearance of inulin is equal to GFR. Several additional points about the use of inulin to measure GFR should be noted. Inulin is not an endogenous substance and therefore must be infused intravenously. The numerator of the fraction, the urine concentration of inulin times the volume in urine flow rate, is equal to the excretion rate of inulin. Changes in plasma inulin concentration do not alter GFR, although examination of the equation might lead to the opposite conclusion. For example, an increase in plasma inulin concentration by infusing more inulin does not decrease GFR according to the following logic. When the plasma inulin concentration increases, the amount of inulin filtered also increases. This will increase the amount of inulin excreted. That is, the urine concentration of inulin will increase. The urine flow rate will remain constant, but the total inulin excretion will increase. Thus, both the numerator and the denominator increase proportionally, and the calculated value of GFR is unaffected. Number 4. GFR, the clearance of inulin, also is unaffected by the changes in urine flow rate, although inspection of the equation might again lead to the opposite conclusion. When the urine flow rate increases, the urine concentration of inulin decreases proportionally by dilution. Thus, the numerator and the calculated value of GFR will be unaffected by such a change in urine flow rate. This is illustrated in the following sample problem. A woman who consents to renal studies in the Clinical Research Center is infused with inulin to measure her GFR. Over the course of the measurement, her urine flow rate is intentionally varied by having her drink large amounts of water. The plasma concentration of inulin is kept constant at 1 mg per milliliter with the continuous infusion. The urine flow rate and urine concentration of inulin before and after she drinks water as follows. Before drinking, the urine concentration of inulin is 100 mg per milliliter, and the urine flow rate is 1 milliliter per minute. After drinking water, the urine concentration of inulin is 20 mg per milliliter, and the urine flow rate is 5 milliliters per minute. Thus, what is the effect of the increase in urine flow produced by drinking water on the woman's GFR? If we calculate the GFR from the clearance of inulin before and after the woman drank water, we'll see that GFR was absolutely constant. As the urine flow rate increased from 1 milliliter per minute to 5 milliliters per minute, urine concentration of inulin decreased by dilution from 100 mg per milliliter to 20 mg per milliliter, a proportional change. Once again, look at the numbers. The GFR before drinking water is the clearance of inulin. The urine concentration of inulin times the urine flow rate over the plasma concentration of inulin. GFR thus is 100 milliliters per minute. After drinking water, the urine concentration of inulin falls to 20 mg per milliliter, and the urine flow rate increases to 5 milliliters per minute. Thus GFR is unchanged and remains 100 milliliters per minute. Inulin is the only perfect glomerular marker. No other marker is perfect. The closest substance identified currently is creatinine, which is freely filtered across the glomerular capillaries, but it is also secreted to a small extent. Thus, the clearance of creatinine slightly overestimates the GFR. The convenience of using creatinine, however, outweighs this small error. Creatinine is an endogenous substance, inulin is not, and does not need to be infused in order to measure GFR. Thus, in day-to-day clinical practice, clearance of creatinine is used to estimate glomerular filtration rate or renal function. Both blood urea nitrogen and serum creatinine concentration can be used to estimate GFR because both urea and creatinine are filtered across glomerular capillaries. Thus, each substance depends on the filtration step in order to be excreted in the urine. When there is a decrease in GFR, that is in renal failure, blood urea nitrogen or BUN and serum creatinine increase because they are not adequately filtered. Volume contraction or hypovolemia results in decreased renal perfusion, as a consequence, decreased GFR or prerenal azotemia. In prerenal azotemia, both BUN and serum creatinine are increased due to the decrease in glomerular filtration rate. However, urea is partially reabsorbed and creatinine is not. Thus, the blood urea nitrogen increases more than serum creatinine. In volume contraction, there is increased proximal reabsorption of all solutes, including urea, which is responsible for the greater increase in blood urea nitrogen concentration. One indicator, therefore, of volume contraction or prerenal azotemia is an increased ratio of BUN to creatinine to more than 20. In contrast, renal failure due to an intrinsic renal cause, such as chronic renal failure or acute tubular necrosis, produces an increase in both BUN and serum creatinine, but it does not produce an increase in the ratio of BUN to creatinine. In these instances, there is tubular damage, so there cannot be increased reabsorption of BUN. The filtration fraction expresses the relationship between glomerular filtration rate and renal plasma flow. The filtration fraction is given by the following equation. Filtration fraction is equal to the GFR divided by renal plasma flow. This equation is given on page 257 of the text. In other words, the filtration fraction is the fraction of the renal plasma flow that is filtered across glomerular capillaries. The value for the filtration fraction is normally 0.20, or approximately 20%. 20% thus of renal plasma flow is filtered and 80% is not filtered. The 80% of renal plasma flow that is not filtered leaves the glomerular capillaries via the efferent arterioles and becomes the peritubular capillary blood flow. As an exercise, think about the effect of changes in filtration fraction on the protein concentration and oncotic pressure of peritubular capillary blood. Once again, refer to Table 6-6. If the filtration fraction were to increase, relatively more fluid would be filtered out of the glomerular capillary blood. This would result in a greater than usual increase in the protein concentration of the capillary blood. Thus, increases in the filtration fraction produce increases in the protein concentration and the oncotic pressure of the peritubular capillary blood. This has consequences for the reabsorptive mechanism in the proximal tubule as discussed later in this chapter. Ultimately, increases in peritubular capillary blood oncotic pressure lead to an increased gradient for reabsorption of water and thus solutes. This concludes this section.